You have your restriction enzyme and essay question on the bottom here that was passed out yesterday? Yeah. Someday. On the bottom here, you have an AP practice question on hormones. This is, I know we've done the second part, which is glucose levels in humans and how that's regulated. Friday, we are going to look at the menstrual cycle and the hormones, all the hormones associated with it. But today I would like to look at another part of how the body regulates various systems, and that's through the brain and neurotransmission and neurotransmitters. So we're going to be looking at that part right now. Okay, so let me put my stuff away so I can play with stuff if I have it. Okay, so we're going to be looking at the nervous system, and more specifically on how the nervous system communicates, right? And this is the master controlling center of the body. The endocrine system was also a communicating system, just like the neurotransmission is a communicating system. This is much, much faster. This is done through electricity as opposed to dumping a chemical into your bloodstream and then looking for target cells for them to initiate change. This is going to be very, very quick, very precise, and some of these travel like almost at 200 miles an hour, so it's very, very quick. Okay, to begin with, we are going to look at the neurons, and then I don't know if we look at, do you guys look at anatomy of the nervous system, like the parts of the brain or not? Okay.
So you cover that as well.
Okay, so maybe I'll cover that. Well, I can do that really quick right now. Okay, so obviously you're going to have the brain here, and it looks like, hey, it's very similar to Jack's brain over there. Hey, you know. All right, so if you think of the brain as your fist, right? And then you're going to have, you know, I don't know if you do terminology very much, but I don't know if it's going to be covered. You have anterior, you have posterior, you have lateral, which means the side, you know, when you lateral football. Yes?
So is this a brain, like from what view?
This is a lateral view of the brain. So it's looking from the temporal side. Right, from this side here. So you're looking at the brain from the side. And, you know, maybe this brain could be a little bigger. Yeah, close enough. Okay, so posterior, anterior, you get inferior, superior, right? I don't know if you really need that, but anyway, it's there. You have the lobes of the brain. There are 4 primary lobes of the brain. You've got the frontal lobe, parietal lobe, the temporal lobe, and the occipital lobe. So this is frontal. Parietal, and oops, I wrote over the other. And then you've got the occipital. Now try to write neater so you can actually read it. You know, it might help. I don't know. Then you got the temporal. Okay, and this is like all third try in the biochemistry. If you want to take the biochemistry, make sure that's really all we look at is the brain. So you got frontal, parietal, occipital, temporal. And down here, you're going to have anyone remember?
Cerebellum.
Cerebellum. And there might be 2 R's in there. Who knows? I don't know. Whatever. Anyway, so general functions for these. Okay. The brain is compartmentalized, which means different areas of the brain are responsible for different things. And one way this is discovered is always, you know, if someone gets injured in the brain, this portion of the brain, or this behavior is inhibited, right? So it's not like you damage part of the brain and everything falls apart. It's compartmentalized, okay? So the frontal part is behavior. So this is behavior, personality, judgment. Okay, and this is the most advanced part of the brain. right? And it's one of the last to develop, as some of you have awesome of this part of it right now, right? So it's not developed, and that was the judgment part. Right? So this is the very last to develop. It's the most, I don't know if you call it superior that we've seen anywhere on the planet, right? This is the most developed, highly developed part. The temporal is going to be, there's many, many things in the temporal. You're going to have smell. You can have emotion, like the amygdala is inward in the temporal lobe. It's going to have identification. So ID, right? Identification. There's like the fusiform gyrus is identified phases only. There's a portion in the brain that just focuses on phases. So identification of objects. The parietal lobe is you're going to have the sensory and motor cortex up here. So sensory cortex, which is, when you touch something, it's analyzed by the sensory cortex, and it says, oh, hot, cold, pressure, whatever, and then signals are sent to other places, say, oh, that was an ice cube that was cold, right? Also up here, so if you look at, this is the sensory cortex over here. Then, directly anterior, in front of, you're going to have the motor cortex. Motor cortex. Okay, so it's basically, if you want to move your hand, the motor cortex is going to send that signal to your hand and move. Okay. Okay. Occipital lobe. What's occipital lobe for? Exactly. Yeah, no one said it, but I'll just say pretend like you guys did. This is for eyesight. Okay. So the signal from the eye goes directly back to the thalamus and LGN and all that stuff. But anyway, goes to the occipital lobe. Okay, occipital lobe is responsible for eyesight. Okay, processing that info. Cerebellum. And since most of you are here, your cerebellums aren't as highly developed as, let's say, no, there might be one that is very highly developed here. She just stood up. Cerebellum is for muscle coordination, it's for coordination. I was just going to say that, like, professional athletes have very, very highly developed cerebellum because, hit an object about this big coming at you 100 miles an hour. That takes a lot of coordination, a lot of fine motor skills, fine movement, and that's what does this. So if you're going down the stairs and you have a hard time, your cerebellum is not as highly developed as some others may be. Okay, so this is like gross anatomy. This is just the big areas here. Obviously, there's a lot of different parts of the brain that are responsible for smaller aspects, like facial identification, judgment, behavior. There's a lot of stuff happening here. Really cool stories on how they found this stuff. But take biochemistry and you can see all this. Anyway, all right, so if we were to make a sagittal cut, which means, let's say if I have this, let's say this is the let me do it this way. The brain is divided into two hemispheres, right? So you got the left hemisphere and the right hemisphere. And let's say you were to make a cut right down the middle and separate the brains out. So it would be a medial sagittal cut, right? And the brain, we're still looking at it from the temporal side. We're still looking at it from the side, the lateral, from the side. Inside, you would see, that's a very bad drawing, anyway, whatever. Inside you'd see, so this is anterior, and this is posterior, so this is the back. The cerebellum would be over here somewhere, okay? Inside, major structures that you need to look at. Major structures are probably the thalamus, okay? This is the major relay station for most all neurons, actually like all except one. So it's a relay station. peripheral. Okay, so there's a relay station for the peripheral nervous system. By the way, the peripheral nervous system and the central nervous system, something I did not talk about. Anyone know what parts of the central nervous system? What are the nervous system? The central nervous system. Yeah, brain. Good. So the brain is the CNS, central nervous system. You got brain, and you got spinal cord. Okay, and then the peripheral nervous system. Peripheral. And I don't know why I just didn't put PNS. This is all the nerves that extend from the spinal cord. Okay? So these are mainly nerves. And what two types of nerves are there? There's sensory and motor. Okay? So these are sensory and motor. So if this is the brain, this could be the spinal cord. Okay? And what I'm saying is that the thalamus, all of the sensory neurons, all the motor neurons go through the thalamus. Okay? And one way it was found out is this, there was this incident where this person called Karen Ann Quinlan, she was wanted to go out with her friends and go to a party and go to drinking, and she had like menstrual cramps, and she's like feeling really bad, but wanted to take these sedatives in order to help her feel better, deaden the pain. But she took too many of those and then drank too much. And basically what happened is that her thalamus was destroyed, and whatever happened, her thalamus was destroyed, and she was comatose. So for 7 years she was in a coma, and her parents said, oh, we got to pull the plug, right? We got to pull the plug. And so they went through court cases, things like this. 19 years later, they pulled the plug. So many years later, they pulled the plug, and she lived. So she didn't die. And then they discovered later, after she died, which was like an just enormous amount of time, that her entire brain was fully functional, right? The only part of the brain that was damaged was the thalamus. So think of this. Think of you being trapped in your brain, not being able to communicate anything to the outside world, and the outside world not being able to communicate, because these sensory neurons, they have to go through here. So any stimuli that would come into you goes through the thalamus. And anything you want to communicate out goes through the thalamus to move your hand, to move your mouth, to whatever you want to do. And think of being trapped in your brain for 19 years, or however long that was. So that's how the thalamus was found, like, oh, that's what the thalamus does. It's a relay station for all this. In the brainstem, there are various, like pons, medulla, all that stuff, but, I don't know. I don't want to go into that much detail. I'd rather go through some other stuff. But these are the vital sensors. Like the pons regulates breathing. Some of these regulate heart rate. So the brainstem is a primitive brain, right? Most creatures, if not all creatures, have these. Basically, you hit someone right in the back of the head, you kill them, right? Instant. Because what happens is these are the vital areas that control heart rate, control breathing, control that, and you hit that, it's gone, right? As opposed to, you can literally put a knife into someone's head, and you only damage portions of it, but they'll be fine, right? I mean, having a knife through your head. And you've heard of many, many stories that people get shot in the head, and they're fine, right? Not that they're fine, but they live, and they're almost normal, like the senator from where?
Gabrielle Gifford.
Yeah.
Gabrielle Gifford.
So anyway, that's the compartment part of the brain. Okay, so good. Okay, general stuff. How do you erase here? Oh, I was looking for that big thing. Okay, so I'm going to erase the whole thing here, and it's on video, I guess. All right, so now we're going to be looking at these neurons that I kind of alluded to in the peripheral nervous system, how these things work, and you might have seen these before. I don't know, in grade school, or I don't know, you might have seen them, or watching PBS. But anyway, so you basically have these neurons that are going to have these little extensions. And it looks like a, I don't know what it looks like, but it looks like something. All right, so very, very bad drawing of these things. But this would be a neuron. And neurons conduct an impulse from the cell body through the axon and through the axon terminal. Sometimes they call these terminal buttons because at the end they look like little buttons. Anyway, so in the cell body you have obviously a nucleus which has DNA. And all the organelles are kept here, right? These are all the organelles. These things are dendrites. Okay, which we'll talk about dendrites and axon terminals in a few minutes. But general anatomy of an axon, pretty straightforward. Impulse always travels in this direction. And some, like in reflexes, in muscles, in eyes, these axons are myelinated, which means that they have these, if you have the axon here, this is the myelin. Anyway, something like, it sounds like this. I don't know if it's spelled that way. Anyway, so here's the axon. Okay, and you've got these like pigs in a blanket, little tortilla wrapped around a hot dog. I don't know, but anyway, this myelin is made out of fat. It's a fatty tissue, which is not necessarily an insulator, but basically it makes the conduction of this impulse travel faster because non-myelinated axons. So you get an axon here, right? A non-myelinated action potential. The signal travels through here, right? In a myelinated axon, the signal jumps from node to node. Anyone know the names of these nodes?
Mendeleev sheaths?
No, that's what these things are called. These are myelinated sheaths. Right? These are myelinated sheaths. So it's a myelin sheath. And the nodes are called nodes of Ranvier. Mr. Ranvier said, I'm going to name it. Give it my name. So these are nodes of Ranvier. Okay? So,
like French.
Sure. Yeah, I'm sure. Who's that? That just doesn't sound good. No, it's the same guy. Nodes of what?
Ranvier.
Oh, you're just saying it wrong. It's Ranvier.
It is French.
Yeah, I'm kidding. Okay, so you're okay with the purpose of the myelination? Is to, not to keep it warm, but to make the conduction faster. Okay? And especially for reflex arcs, like things that are literally going to save your life or going to save your limbs from being cut off, these are myelinated. So you want a reflex arc to go really fast, right? You don't want to think about it. Say, yeah, I probably should move my arm there because it's burning. You know? So they're generally myelinated, these reflexes. All right, so next thing, we're going to go through conduction. How does an impulse travel through this axon? Okay? Enormous amount of detail. Keep with me here. If you have questions, keep it to yourself. No, I'm kidding. Just answer questions. I mean, raise your hand. All right, so we're going to be looking at the axon, just the axon. And the axon, hey, before you start drawing, can you wait, like, give me a couple seconds to draw stuff, because what I do is I draw it, then I erase things, and you're like, oh, come on. You know, I've heard this over and over again. So, I'm going to erase these right here, because they're going to have channels. They're sodium-potassium gates. You guys remember those?
Yeah.
Okay. Now, there's some that have actually sodium gates and just potassium gates. Then there's the sodium-potassium pumps. Okay? So, let's say we've got and I'm just drawing these open, but they're not always open. Some are actually always open. Let's call these sodium gates. Okay? And we'll call these potassium gates. So K gates, potassium, and sodium gates. Okay. Now, in the cell, right? The cell that I'm talking about is a neuron. And I'm only looking at a partial of the neuron. So if you got the whole neuron here, we're only looking at this portion right here. Right? We're only looking at this portion right there. Okay? All right. There is an action potential. There's a concentration gradient created here. And the concentration gradient created is what is going to give you that difference in charge, that action potential, the difference in charge. So the difference in charge is normally in your computers, what is that difference in charge in? What's it measured as? What is it? What's inside those wires? Volts, but what are volts? What is that? What are you measuring? Yeah. Okay, what is electricity? Electrons. Great. Okay, so it's electrons, right? So obviously there's a positive and negative, and that's the difference in charge, different in potential. Right? They're going to go from negative to positive. Here, obviously we don't have electrons, right? These electrons are a little damaging, antioxidant stuff. They're bad. The electrons are not good to be free, right? They need to be sequestered and things like that. Anyway, so what's the action potential? How the action potential is created here are by these ions, right? You've heard of electrolytes. You look at the Gatorade and there's all these chemicals in there. They call them electrolytes. Some of these electrolytes, that's what they're for. They're for signal conduction in your axons. So some of these, which you're very, very familiar with, are obviously sodium. Some of them are potassium. Okay? So let's create this action potential by differing the charges on the ions. So on the outside, I'm going to do it red. There's a lot of sodium out here. Okay? Sodium. They're all over. Okay? Which time? Okay, so you have sodium here. Okay? And, oh my gosh, there's supposed to be little a, by the way. Sodium is, make sure. Okay, I table here. That's why I got it wrong. Yeah, that's it. Okay, so there's sodium on the it takes hold now. It's going to drive me crazy. Anyway, little A's on the sodium. There's some sodium in here, but not much. Okay? Now, initially, the sodium is pumped out of there, right? Initially. All right. Now what we have is potassium. There's potassium on the inside. There's more potassium on the inside than there is the outside. But you're saying, wait a minute, that gives you a positive charge outside and a positive charge inside. Hold on a minute. All right. On the inside, there's the ion that complements sodium all the time. What's that one?
Chlorine.
Okay, chlorine. So there's a lot of chlorine on the inside. Okay. And there's also these proteins on the inside. So we'll call these proteins. And these proteins have a negative charge. Okay? In effect, you're going to create this action potential where the inside is going to be negative and then the outside is going to be positive. Okay, that's generally what happens here. Out here, it's positive, negative, positive. Okay, yes?
What is this all happening inside of?
The axon.
Okay.
This is the axon, so yeah. So here's and then the terminal buttons. Oh, looks like it's that over here. Okay, so, okay. All right, this is called, where no impulse is passing through, this is called the resting potential. Resting potential. Okay? The resting potential, and let me show you a little graph here of how we're doing this. basically you put electrodes measuring the outside from the inside. And they found that the difference in potential was negative 70 millivolts, right? So let's say this is our 0 here, 0 millivolts. And let's say that this is, what was it, 90? I don't know. Oh, 30, whatever. 30 millivolts, okay? So, what is going to happen is that at resting, you're going to have no impulse, right? And then, there's going to be a stimuli coming, like someone hits you or someone does something, right? You feel something, right? Then you're going to have a change in charge, a change in potential, okay? And obviously that's going to send a signal down, and it's going to come back down, but it comes below minus 70 millivolts. It actually goes down to, let me bring this down a little bit, sorry. Let's say it goes down to minus 90 millivolts. Okay? So it goes down to minus 90 millivolts. So it's going down below. Anyway, so it goes down to minus 90 millivolts. And then it kind of comes back up. Okay? All right. So what we're going to do is follow this. Right now, we're at minus 70 millivolts. Okay? And understand there's a threshold. If a piece of dust lands on you, are you going to feel it? No. There's probably, so what happens is there's a threshold of pressure or a threshold that the nerve is going to need in order to send an impulse. So imagine if you could feel every dust particle that falls on you, you'd go crazy, right? Because all these signals are coming into you like, oh, that would be, yeah, just like that. Okay, so, right now, minus 70 millivolts, this is called the resting potential. Good?
Okay.
All right, so we're right here. That's the resting potential. So RP. All right, then, what happens is there's an impulse sent, right? Something stimulates you. There's an impulse sent, and this impulse is, let's say it's a motor neuron. No, it's a sensory neuron, so where's it going? To the parietal lobe, the sensory cortex of the parietal lobe, through the thalamus, all that stuff. Okay, so what we're going to do is this. Sorry about this, but you're going to draw this whole thing over here.
Awesome.
Okay, and then you're going to erase the little doors here. Okay, so what's going to happen? I'm only going to abbreviate this. I'm not going to draw everything here, but understand they're still here, right? I'm only drawing the difference between this resting potential and the start of this impulse. Okay, so anyone know what's going to happen next? What happens? Curious. No. Well, the doors do open and close, but let's not worry about that right now. Okay, yes.
Electrons.
Wait, no electrons. No electrons here. Electrons are bad. No electrons. Right? Yeah. Wait. What? Okay. Time to explain. Let me finish this because I'm going to run out of time. But, yeah. So you're going to have to look at neurotransmitters and things like this. Whoa. Just hold on. Then you got sensory receptors up here. Too much. Too much. Hold on. All right. All right. So what you want to do is, right now it's backwards, right? And it should be positive, negative, positive. So what's going to happen is something different, not expected, but basically what you're going to have is you're going to have potassium, through the potassium channel. Sorry, I drew this on the wrong side. Anyway, through the potassium channels, the potassium, anyway, K is going to rush out. So I'm just drawing the same line with K coming out. So there's going to be a lot of K on the outside. K, and sorry, it goes through the potassium channels only. They're selectively permeable. Okay? So there's going to be a lot of potassium out here, potassium out here, potassium out here, potassium out here. Initially, it's going to repolarize the axon. So it's going to go, right, it just depolarized it. Now it's going to repolarize it, making the inside negative, the outside positive, and this is repolarization. So this is called repolarization. Repolarization. Okay? Now you can see that the charge inside is going from positive to negative. Okay? So right here is this area right here. So this is depolarization, this is repolarization. Okay? Alright? But notice that there's a dip in the charge here. It started, the resting potential was minus 70 millivolts, but this overshot. It overshoots that resting potential charge. Okay? This actually, what happens here is that this is called a refractory period. Okay? So I'm just going to say refractory. And basically what happens, more potassium is pumped out than needed. Okay? So, more K is comes out than needed. Okay? So that's, in the refractory period, that's number one. Number two, the reason it does this is to kickstart the sodium-potassium pumps to redistribute the charge, these ions, where they should be. So it does this to, this kickstarts the KNA pumps. Okay? And basically what this is going to do is, you can see that they're backwards right now. The sodium should be on the outside, and the potassium should be on the inside. So the refractory period is going to kickstart the sodium-potassium pumps to reestablish that action potential concentration of those ions.
Can I remind you guys that this is the classic example of co-transport. Remember, co-transport, two molecules being transported by a protein pump at the same time, two coming together. This is one that I think the AP is most likely to reference. This is the example of co-transport.
So is it 2 to 1? Like 2 potassiums to 1 to 2? What is it?
3 to 2.
3 to 2. Which is 3? Anyway, sodium is 3? 2.
No, 100% sure. I think it's 3.
Yeah. And I don't know if you need to be that detailed, but understand that the sodium-potassium pump is going to take, let's say, 3 in and 2, 3 out, 2 in. Right? So this is a sodium-potassium pump that is going to reestablish the concentrations to have that refractory period. Resting potential. Okay. So, okay, once that is done, you are at the resting potential again. So this is resting potential. Okay? And by the way, this is an all or none type of signal, right? Once you get this impulse going, it doesn't stop, right? Once you get it started, there's no turning back. So this is all or none. Either it happens or it doesn't. And once it happens, it goes through this every single time. Okay? So at each portion, it's getting depolarized. So this is negative, this is positive, and this section is positive, and this is negative. So what's going to happen, it's going to, this positive charge is going to initiate a change over here, and it cascades all the way through. So it changes. And it does this is a 3 millisecond instance. So in 3 milliseconds, this is what happens. Okay? So it's like 1 millisecond, 2 milliseconds, 3 milliseconds. And you're ready for the next one. So 3 milliseconds. It's very fast. You know, the saying is travels at 180 to 200 miles an hour. Okay. Good? And just in time for one more thing. Yes?
So this is just for the myelinated sheets?
No, this is for both.
This
But
is for all
basically
of
what
them.
happens is, in the myelinated, this happens at one node Rambierre, and then it jumps to the next one. And then this happens in the node Rambierre, and then it jumps. Okay, so I'm going to erase all this. Okay, we're going to look at the terminal button, and that'll end it. Don't worry, in biochemistry, we spend like a whole class on this as opposed to like 15 minutes. But then, this class really prepares you for that biochem class. Alright, so, this is a terminal button. This is an axon terminal. Okay? By the way, the heading on all those pictures that we just drew was an action potential. So if you could put the word action potential, I never put it up here, right? I don't think I did. But that's an action potential. Okay, this one is called neurotransmitters, like the transmission of the the transmission of the electrical signal from axon terminal to dendrite. So, oops, let me go a little bigger. You've probably seen these on commercials where you have a Lunesta, I don't know, what's the one where they say the signals and the things go by to the other side? That commercial. You should watch more TV. Anyway. Alright, so, here we go. Oh, okay, so, this is an action potential, right? That's an impulse traveling through. Okay, so here we go. Sorry, I'm erasing things. You're going to have gates on the side of these. These are called calcium gates. Inside here, you've got these vesicles. And inside the vesicles, so these are vesicles, you've got these neurotransmitters. Okay, and they could be like dopamine, serotonin, acetylcholine. And what's really interesting, and I do a little portion of this, the drugs like cocaine and methamphetamines mimic some of these neurotransmitters. So they act like neurotransmitters. Dopamine is the happy one, right? A lot of dopamine, you're pleased, you're happy. So cocaine works on that guy and it works on the reward system of the brain, which is another part that we get into next year. All right, so ready? Here we go. We got the anatomy. This is a terminal button. This is a dendrite, so label those in case you didn't. This area right here is called a synaptic cleft. Sometimes called it just a synapse or the synaptic cleft. The cleft is like a bridge, an opening. So this is a synapse in here. That's an S, by the way. Synapse. Okay, so ready? Here goes. When an impulse travels, calcium gates open. Little calcium molecules enter. Okay? So this equals calcium. So it's oh my gosh, it's a 2 plus. Okay. So calcium gates open. Okay? When the calcium gates open, they travel to the vesicles. So let's pretend these calcium are really green. Okay? What they do is they attach to the vesicles. So these are calcium. So these calcium ions. And by the way, your bones have calcium, right? So when calcitonin, parathyroid hormone, remember that? When you need calcium, this is what it's for, right? So calcium is like not only for your bones, but unbelievably important for neurotransmission. This is basically who you are. This could be right here. This is the thought of like, oh my God, what's this guy gonna finish, right?
That's the thoughts going through your mind. And you need calcium gates to continue that thought to your dopamine level, saying, it's going to be soon, so you're happy, right? So dopamine's released, saying, oh, that sounds great, look, 2 minutes. Okay. See, so calcium is really important. Anyway, so calcium is going to attach to the vesicle. The vesicle is going to travel to the membrane, right? This is just a regular phospholipid membrane, and the vesicle is made out of a phospholipid bilayer. It's going to travel right here, and it's going to blend, or it's going to attach to this thingamajig here, and it's going to spill out the neurotransmitter. What is this process called? Yeah. Yes, exocytosis, right? Exocytosis, this is something that's, I'm sure it's going to show up there somewhere. This is exocytosis, so it literally takes energy for it to do this, and it's going to be initiated by this calcium binding to the vesicle, and it travels to the end, dumps its neurotransmitter out, and on here, there are these little gates here. We'll call these, let's call these sodium gates. You might have heard of sodium gates before, right? Yeah, maybe like 30 seconds ago, we talked about the action potential. Okay, so these sodium gates have these receptors on them that are for the neurotransmitter. Let's say this neurotransmitter is now red. Oh my goodness, mixing up all the colors. This neurotransmitter binds to the sodium gates and opens the sodium gates. What happens when you open sodium gates? Yeah. Jeez. Yeah. No. What happens when the sodium goes through it? Really? Huh. So if I were to have water in my sink and I take the plug out, water goes through? Yeah. Okay. Amazing. I see why you're in DC calcium. Okay. What's your name again?
Henry.
Henry, what happens?
Well, if the gates are open, they're going to start flowing out. The potassium's going to start flowing. Oh wait, the sodium's going to flow in. The potassium's going to flow out, and it's going to do that reverse polarity.
What do we call this thing? Depolarization. Okay, depolarization. What's the name that I asked you to put on the previous picture? An action potential is going to happen. This is how an impulse is generated between one axon and the other axon. Okay? So, the electrical signal, this action potential, cannot travel through the synapse. There's a gap here. It's like you've got a wire for your computer and you cut the cord. Your computer's not going to work. So you need something to bridge that gap. What bridges that gap is this neurotransmitter. Okay? And that's the end of that. We're done. Wow. Take by the transport molecules through endocytosis. So basically, endocytosis.
What type of endocytosis?
The good one. Cytosis. I don't know, what type of good one is that?
Phago.
Is it the grab a hold?
Oh yeah, they do. They actually grab a hold and bring them in. So cell-mediated.
Receptor
Receptor-mediated. Yeah, that one. Yeah, that one. Enzymes come and destroy them. They come and break them apart. Right? It's really bad for neurotransmitters to come here. Like serotonin. Serotonin changes your mood. Sometimes when there's too much serotonin in here, you get depressed or you're sad. So Prozac comes in here and like closes these up and they makes, you're okay. So they're not good. They can't sit there. Bad things happen when they sit here, right? A lot of bad things happen when they sit here. Okay, that's it. For real.